This video is on graphing transformations of function. This is part one of 3 videos. In this particular video, we'll look at how numbers in various places in a parent function equation is going to consistently change the graphs and its features. So, inherent in that is the understanding of what a parent function is. A parent function is the most simple function of a family of functions. So basically, all the functions or all the graphs that have the same shape all belong to a family. So at this point, we kind of have 6 parent functions that we've talked about. The one that I don't have on here is the linear function. I don't have the linear function on because it's a little bit, I guess, just a little bit different. Moving a linear function up and down could also be described as moving it left or right because it just has a constant slope. So it makes it both easier and more confusing. So as a result, I've removed it. So we're just going to focus on these 5. The absolute value, which is the v-shaped function, and that is this y equals absolute value of x. The quadratic, which is y equals x squared. Cubic says it right here, but it's pretty small. So this is just y equals x to the 3rd power. That's cubic. Then there's square root y, or f of x, equals square root of x. And then cubed root, which is different than cubic. That has that radical symbol with the little 3 nestled in the check mark. That's cubed root of x. You should know these graphs by their appearance. You should know that once I give you an absolute value equation, it's going to be v-shaped and it's going to be some transformation of this. We can make all these graphs by creating a simple table of values, right? If I wanted to make the absolute value graph, I would make a table and I would want to know x versus the absolute value of x. And I would just pick values. This is -1, the absolute value of -1 is 1. If x is 0, the absolute value of 0 is 0. If x is 1, the absolute value of 1 is 1. And that's how I get these points. There's no magic there. It just comes from a simple table. What ends up happening is that you do this so many times that some very basic points end up sticking with us. It ends up that all of these graphs have 2 points in common, and those 2 points in common are 0, 0, and 1, 1. And I can see here's 0, 0, here's 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Because they have those 2 points all in common, we're going to use those 2 points to help us in writing equations of graphs and also in helping us graph them. As a result, also, it's very important that we know at least 1, if not 3 additional points, so I can differentiate between all these graphs, right? If they just only had these 2 points, they would all be the same. So it's this 3rd point, or even, 2 squared is 4, -2 squared is 4. That makes this graph different than this one here. It makes quadratic different than absolute value, because absolute value of 2 is 2, whereas 2 squared is 4, so that makes this one curved. Whereas here, 2 to the 3rd is 8, so that gives me that there. All right, so keep those things in mind. No magic, it's just about making a table of x versus whatever we're doing to the x. Okay? Very good. So how can we transform a function? There's 6 things that you can do by adding a number in various locations to the parent equation. We can reflect over the x-axis. Will be if we negate the function that we're working with. We can do a vertical stretch or compression. This is if we put a number out in front of our function. We can translate left or right. This is if we put a number inside our function attached to the x. We can translate up or down. This is if we put a number outside of the function, not attached to the x, attached to the y. We can do horizontal stretches or compressions and reflections over the y-axis as well. For our sake, we are not going to cover these in this course. Reason being, any horizontal stretch or compression could also be described as a vertical stretch or compression. And we just don't need to get into the reflections over the y-axis. So I'm going to let you know that we can do those things. But we are not going to cover those in this course, at least not this semester. So those are the 6 things. We'll go into each of these in more detail in just a couple minutes. It doesn't matter what parent function is. The location of this number or this sign is consistently described the same way. Okay, so whenever I put a number at the end, it's always up or down, regardless if this is an x squared or a square root of x or an x cubed or etc. Okay, so let's take a look at how this works. First thing that we can do, so we'll look at each of these separately. I'll show you how it applies to a graph. I'll give you an equation. We'll go from there. We could reflect over the x-axis. We said this happens if there's a negative in front of my function. And how do we apply it? So basically we're going to multiply the heights, the y values of each point by -1, or basically we're just reflecting each of these points over the x-axis. So I chose f of x equals negative square root of x as my function. So as a result, I'm going to start with the graph of the parent graph, which is square root of x, right? This is in the parent function, parent family of square root of x. I want to take this and I want to reflect it. Now, because we can reflect over y, even though we're not going to, I want to say that I'm reflecting it over x. So let's do that. If I take this height and it's on the x-axis, so if I try to reflect it over the x-axis, it doesn't go anywhere. So it's going to stay put. If I take 0, the y value of this point, and multiply it by -1, it goes nowhere. This point on this graph is 1, +1. So if I take 1, +1, I take the y value right there and I multiply it by -1, I get -1. So my new point would be 1, -1, which is right here. Now I can see that's just this flipped over the x-axis. The next exact point that I have, when I exact I mean integer values, is 4, +2. So we said to reflect, take the y value, multiply it by -1, and I get 4, -2. So I want 4, -2. This point reflected over the x-axis. That's 3 points. That's enough for me to get my shape. I'm going to do the best I can here to mimic the overall shape. I missed my point there, but you get the point. So this is negative square root of x. Nope, 0, 0 doesn't reflect, right? It's on the axis, so because it's on the axis, it will never reflect. That will be very helpful for us in the future. It's going to mean that I can take that starting point, and wherever it's located on my graph, it's going to help me to figure out how far left or right or up or down I've been, because it will never be reflected or stretched. The next thing we could do is we could vertically stretch or compress my graph. So that's when I have a number out in front of my function. If that number is the absolute value of that number, because remember, the negative just means reflection. The actual quantity of the number is going to tell me if it's been stretched or compressed. So if it's made taller or shorter, right? That's all that means, stretch versus compress. So because this guy right here is between 0 and 1, my graph is going to get shorter, closer to the x-axis. So this is a vertical compression by 1/2. Okay, so how do we deal with that? Well, vertical changes, which reflections and stretches and compressions are, tell us to multiply the y value, the height of each point, by whatever that number is. Okay, so I'm always going to start with the 0, 0. It's one of the points that all the graphs have, so I'm going to start there. If I take 0, 0 and I multiply the y value by the number out in front, which we call a, so that's 1/2 here. If I take that and multiply it by 1/2, it doesn't go anywhere, right? 0 times 1/2 is just 0. So 0, 0 stays put, just like I mentioned in the last video, or the last slide, excuse me. Next, I move on to the next point. So I'm just transforming each point. I'm not doing the overall graph. I'm thinking small. So I want to take this y value and I want to multiply it by 1/2. So 1/2 of 1 is 1/2. So I want my new point to be 1, 1/2, which is right there. Okay? I'm going to take my next point. This is the point 2, 4. 2 squared is 4. That's why that's the point. I'm going to take the y and I want to multiply it by 1/2. If I multiply 4 by 1/2, I get 2. So this new point is going to be 2, 2. So 2, 2. Same thing over here. Take this height, 1, multiply it by 1/2, becomes positive 1/2. So I'm going to be at -1, positive 1/2. -2, 4. Take the height of 4, half it. 1/2 of 4 is 2, so it comes down to a height of 2. So you'll see when I multiply it, I'm not moving it down 1/2. It's not an up or down. I'm halving the height. So my new graph is going to look something. Actually, let me switch my color here. so it stands out more. So I want to take my graph and it's going to go through these new points. So it goes through there, I keep going, it goes up through here. It keeps this rounded U shape. I always do better going to the right than going to the left. And something like that. Okay, so this is 1/2 x squared. And again, I started with this red curve because this is the parent graph of x squared. So that's where I start, and then I just took all the heights of those and I halved them because that said to vertically compress it by 1/2. Again, 0, 0 doesn't stretch or compress. So that's a very important point for us. The next thing that we can do, we can translate our graph left or right. We said we see that if there's a number inside the function with a attached to the x, and left or right. So if I see a plus in my equation like I do here, this means that I'm going left. This is the one that's opposite of what we think it should be. Plus means left, minus means right. Okay, that's the same as with all the functions. What we're going to do is we're going to figure out what the parent is, graph the parent, and then literally just count left or right, however many we need for our description. So based off of these guys here, I know that my parent is the absolute value of x. So I'm going to graph absolute value of x. Now I've already taken the time to do that. So this is the parent graph, y equals the absolute value of x. And then these guys are pretty straightforward in terms of the graphing. I want to take each of these points and literally count left 2. Just be careful to scale here. Kind of the smaller boxes are each 1/2. So left 2 would put me here. Left 2 would put me here. Left 2 would put me here. I'm literally just counting each of them. Left 2. Left 2. It's still going to be V-shaped because it's still in the absolute value family. Now it just needs to connect to these points. So this is y equals the absolute value of x plus 2. The absolute value graph moved left 2. Okay, there's that 0, 0 point. It got moved to here. It got moved left 2. So if I had the graph here, I would look for that 0, 0 point and figure out how did it get moved from 0, 0. Because it's at -2, 0, I know that I got moved left 2 and not up or down at all. Next, we can move things up or down. This is our last one. So I have a plus k, so there's a number added to the end of the function, outside of the function, outside of the square or the absolute value or the square root or the cube root, etc. This goes with what it looks like. So if I see a plus, it's going up. If I see a minus, it's going down. How do I apply this? Literally count all the points, the parent function, up or down, the amount from the equation. So this right here, red, this 3 is telling me that the parent is cubic, x cubed. So that's where I got these points from. I did my table for x cubed, where I just remembered it went through 0, 0, 1, 1, -1, -1. Then this guy here at the end is outside, oops, sorry about that, whoa, is outside of my graph. Oh, I have no idea what just happened there. That's crazy. Here we go. Okay, there we go, back. Okay, so now this thing outside, this is outside, it's minus. So this is telling me my whole graph, did it again, my whole graph is going down 1. So I'm literally going to take each of these points and count them down 1 and put my new point. Down 1, new point. Down 1, new point. Now this is the trickiest one to graph. This is in the cubed root. I want to start that middle point, this turning point. From the middle, kind of curve up towards the next one and then curve down towards the one to the left. So it keeps that kind of curve shape. So this is y equals x cubed moved down 1. Okay, and again, that point right there is 0, -1. So I can see from 0, 0, it's been moved down 1, and that's evident in my picture. That's each of the 4 things that we could do. In part 2 of this, we will put those all together and see what that looks like.